This is a so-called Epr protocol. And with all our preparatory work and experience, it will almost take longer to explain this name than explaining the protocol. Well, EPR stands for Einstein, Podolsky, and Rosen. And they introduce what we nowadays understand are simply maximally entangled states of quantum systems to illustrate what were possibly problematic features of quantum mechanics considered at the time, such as spook reaction at a distance. Now we understand that entanglement is really a key feature of quantum mechanics, and we exploit it all the time. And we can indeed utilize entanglement also for quantum key distribution, as has been proposed by Eckert. So for this we are going to use maximally entangled pairs of quantum bits, so Bell pairs, for instance, prepared in this state here. So this is just a Bell pair that we have utilized many times before, but what is interesting is that it can also be written and hence interpreted in a different way. Namely, we can write it also in this way here. This still looks like a maximally entangled state, but written in a different basis. Namely, again, the basis of states plus minus, which is simply the basis of eigenstates of X. While up here we of course just utilize our computational basis states, and these are eigenstates of Z. Let us check whether this indeed works out. And for this I'm going to introduce these definitions simply at these positions here. Now whenever we multiply the plus state for the two quantum bits, we can really multiply this out rather directly. We will have 1 over square root of 2 coming twice, and then all these superpositions occurring with the plus sign. And when we now turn to these states with the minus, then we get a similar sum with factors of 1/2, but in 2 of these cases here in the middle, including a minus sign. And now some of these terms simply cancel, and the remaining states add up to the desired states here. So this works out as intended. To utilize this now for quantum key distribution, we assume that Alice and Bob have created many of these Bell pairs here. So they have many of these pairs, each consisting of 2 quantum bits. Each of these pairs are independent, but within each pair we have entanglement, simply described by this state here. And that's really the same Bell pair in each case. All that we are going to utilize is that this Bell pair has 2 different interpretations. So they generated these Bell pairs at some point, but now are in possession of 1 of the quantum bits of each of these pairs. And now they're going to carry out random measurements. So in this case, both Alice and Bob carry out random measurements independently of each other. And these are again measurements using the observable related to X or to Z. So maybe Alice carries out this sequence here, and Bob carries out this sequence here. But this is really independent of each other and random. So they obtain outcomes 0s and 1, and these will now again be identical whenever they have the same symbol here, so carried out the same measurement. And this is now independent on whether this was a measurement with the observable X or Z. So if they have 1 of these pairs actually measured in X, again the outcomes will be identical, And this is simply because this build pair here is a maximally entangled state, also in the measurement basis of X. So again, at the end, all that Alice and Bob need to do is to share some information, possibly in public, and this is now just the type of measurement that they have carried out. And again, when these measurements were identical, they keep the corresponding bits for their key, which we would not know, so I'm not even going to specify it here, but these could be zeros or ones. So this is secure again in the combination of two aspects. And the first one is just as in the other protocol, because all that Alice and Bob are sharing are the type of measurement. So just sequences of X and Z, and these do not correspond to the measurement outcomes that they have, so they're completely independent of this. And secondly, when one wants to intercept one of these quantum bits, well, this is even more fascinating, because in all of these cases, these quantum bits have been prepared in exactly the same state. So one does not even need to manipulate the quantum bits depending on the key that one obtains, but the state that one deals with is always the same. So this protocol again uses the randomness of quantum measurements, but now on both sides. And on top of this, it uses entanglement to obtain strongly correlated outcomes. And these correlations are of a deep quantum nature, which helps to make this protocol secure. What is the same in both protocols is that Alice and Bob end up with the same key. And this they can now simply use as a symmetric key. So Alice takes her plain text and encrypts it into the ciphertext. For instance, by just adding the key bit by bit modulo 2. And Bob is then just going to use the same key and add it again to the ciphertext to decrypt the message and obtain the plain text. And what has been eliminated is the necessity for Alice and Bob to share this key in a way which is possibly not secure. So these protocols certainly can help to make communication more secure, and they have indeed been realized in the real world many times, for instance using the states of polarization of photons. In that case, the measurement basis Z could correspond to states of polarization in a horizontal and vertical direction, while the measurement basis X would simply correspond to states of polarization rotated by 45 degrees. And these different states of polarization can then be detected by just using some beam splitters. These protocols can also be extended and other protocols devised to make them secure against other types of attack. For instance, situations where somebody tries to impersonate Alice or Bob. So we could think about quantum versions of digital signatures. But for us, our discussion of quantum communication really ends here. Indeed, we have covered all the main ideas, and so we can turn to a new topic. And this topic is just as central for this course, namely now we turn to quantum computation.